Welcome once more to the dark. Tonight, imagine a spider's web stretched across a room, threads connecting at crossroads, walls of silk, and vast empty spaces between. Now replace the room with the universe, stretch each thread to hundreds of millions of light years, and place yourself inside it, resting on one of its strands. I want to walk you back through 50 years of quiet map-making, the slow work of plotting galaxy after galaxy, until a hidden shape rose out of the dark, and show you that you are not adrift, but woven into a vast and ancient web. Before we go further, if this journey means something to you, leave a light behind, so others can find their way here too. And now, lower the lights, put on your headphones, and let the room fall away. We're going to trace the shape of the universe itself, galaxy by galaxy, thread by thread. You're already inside it. You have been your entire life. The web has always been there, invisible, patient, holding everything in place. You don't need to do anything but listen. Let your breath slow. We'll follow the filaments together, and by the end you'll know exactly where you are. I have spent longer than I can remember mapping these distant places, tracing the shapes that light and gravity have made across 13 billion years. I am the cartographer of the dark, and tonight I am here to show you where you are. You are not floating in empty space. You are caught in a web. The universe is not a featureless void with galaxies scattered at random. On the largest scales, matter is organized into a vast network of filaments, sheets, nodes, and voids. A structure called the cosmic web, the Milky Way, with its 200 billion stars, is one small node in that network. The universe has a shape. It has always had a shape. And tonight you are inside it. Most of the universe, by volume, is almost empty. The voids between the filaments occupy roughly 4/5 of all space, but contain only 1/5 of its mass. The web is the exception. The dense threads where galaxies gather, where stars form, where light travels from one cluster to the next. And we live in it, not above it, not beside it, in it. Think of the Milky Way as a single droplet of water clinging to a thread of silk. The thread stretches hundreds of millions of light years in either direction. Other threads cross it at distant intersections, forming knots where thousands of galaxies gather. Between the threads there is almost nothing. Silence. Darkness. Void so empty that a traveler crossing one would encounter fewer than a handful of galaxies across a distance wider than 100 million light-years. You are in a thread, not a knot. Not at a major crossroads. Somewhere along one of the connecting filaments, far from the densest regions, far from the emptiest. The web itself is mostly invisible. What we see, the galaxies, are just the places where the invisible scaffolding is densest. The threads are made primarily of dark matter, the gravitational architecture that attracts ordinary matter. Gas and galaxies accumulate along those dark matter structures like droplets of water on a spider's web after rain. Half the ordinary matter in the universe is not in stars or galaxies at all. It is invisible hot gas stretched between the galaxies, filling the space along the filaments. Warm hot intergalactic medium, at temperatures between 100,000 and 10 million degrees. Too diffuse to see with optical telescopes. Too hot to be cold. Too cool to glow in X-rays, except where the filaments are thickest. This gas carries as much mass as all the stars and galaxies combined, but it announces itself only in whispers. The web is patient, it does not announce itself. For most of human history we did not know it was there. The voids are not truly empty, but they are emptier than anything we have a right to expect. A sphere of space 500 million light-years across, containing perhaps a dozen galaxies where thousands should be. The local void, the nearest of these great silences, spans 100 million light-years and sits just beyond our local neighborhood, close enough to influence the motion of our own galaxy, a gentle repulsion from the emptiness, a slow drift toward denser regions. The silence between the threads is not empty. It is a void hundreds of millions of light-years across, containing almost nothing. And those voids make up most of the universe. The first hints of the web came from counting galaxies near known clusters in the late 70s. Then, in 1986, a single slice of sky containing thousands of galaxies revealed that the universe was not smooth. It had walls, filaments, and vast empty spaces between them. But that discovery belongs to the next rung. For now, let the image settle. The universe is not smooth, it is threaded. And the threads are old. Older than the oldest stars. Older than the first galaxies. The web began to form when the universe was less than 1 million years old. And it has been growing ever since. 13.8 billion years of gravity pulling at a pattern that was 1 part in 100,000. 1 part in 100,000. That was the difference between where the web would grow and where the void would be. Gravity did the rest. Lower the lights, put on your headphones. Because the web is where you have always been. Every photon that reaches your eye has traveled along or across its structure. Every atom in your body was forged in a star that formed along one of its filaments. The web is not a backdrop. It is the architecture that made everything possible. And tonight, we are going to walk its threads. We are going to see how it was found. How the first maps, built from the light of 18,000 galaxies, turned a suspicion into a certainty. How decades of confirmation followed, surveys that mapped hundreds of thousands of galaxies, and showed that the web was not an accident of one region, but a fundamental feature of the universe itself. How it grew from the faintest ripples in the cosmic microwave background, temperature variations so small they were almost beneath detection. How computers reproduced it from the laws of physics alone, starting from the conditions of the early universe and arriving, 13.8 billion years later, at something nearly identical to what we observe. We are going to see the longest filament ever photographed, a thread of hot gas 50 million light-years long, captured in X-ray light. We are going to see the largest known structure in the observable universe, a wall of galaxies 10 billion light-years across, if the data is right. And we are going to locate you within it, not as a coordinate, as a place, because the web is not empty space with galaxies added, it is structure. Ancient, patient, the scaffolding that made everything. The voids are not nothing. They are the space between the threads. The filaments are not random. They are the places where the invisible became visible, where dark matter drew gas into light. You are in one of those places. One small node, in one long thread, in a web that took the age of the universe to weave. The web is still growing, the filaments are still pulling matter inward. The voids are still expanding, pushing galaxies away from their centers toward the denser walls. The structure is not frozen. It is alive with motion, with galaxies streaming along the threads toward distant attractors, with gas cooling and stars forming in the densest regions where filaments intersect. But the motion is slow, measured in millions of years. Measured across distances so vast that light itself takes hundreds of millions of years to cross from one side of a filament to the other. Filaments commonly stretch 500 to 800 million light-years. Threads of dark matter and gas and galaxies woven across a span wider than anything the human mind was built to hold. So for tonight, the web is still, and you are inside it. Not lost, located. One thread among countless others. One node in a network that spans the observable universe. The web did not form around you, you formed because of it. The gravity that pulled the first clouds of hydrogen into the first stars was the same gravity that shaped the web. The dark matter that makes up most of the mass of the universe clustered first, unaffected by light or heat, forming the skeleton. Ordinary matter followed, falling into the valleys carved by the invisible, lighting up the structure from within. Liniakea, our home supercluster, 500 million light-years across, is itself one node in a larger web. The local group, the small cluster that contains the Milky Way and Andromeda and a few dozen smaller galaxies, sits in or near a filament. Not at a crossroads. Not in the deepest void. Somewhere in between, a thread. And that thread connects to other threads, and those threads connect to others still. The web has no center, no edge, no beginning or end that we can see. It simply is. Tonight, you rest inside it. I wonder where you are right now. What city? What hemisphere? What patch of sky overhead? The stars look different from every place on Earth. If you'd like, leave your city below. I'm curious where this voice is reaching tonight. In the late 1970s, astronomers began counting galaxies near known clusters. They pointed their telescopes toward the Perseus cluster, toward the Coma supercluster and its neighbor A1367, expecting to find galaxies scattered smoothly across the void like dust. What they found instead were hints of something else. Galaxies clustered in ways that suggested threads, walls, boundaries where the count dropped to almost nothing. The distribution was not random. It had edges. It had structure. The universe, it seemed, might have a shape. In 1977, a team at the Center for Astrophysics in Cambridge began the first systematic attempt to map the large-scale structure of the cosmos in 3 dimensions. Not photographs, not catalogs of bright points plotted on the flat dome of the sky. 3 dimensions. Distance, direction, and depth. They called it the CFA redshift survey. To measure a galaxy's redshift is to measure how fast the expansion of space carries it away from us. And from that recession speed you can infer distance. One galaxy at a time, one spectrum at a time, they began to build a map of where things actually are. The work was slow. Each galaxy required a spectrum, a fingerprint of its light spread into wavelengths. Each spectrum required hours of telescope time under dark skies. Each measurement was a single point added to a growing 3-dimensional grid. By the early 1980s, they had measured hundreds of galaxies. By 1986, they had enough to plot a single slice of sky, a wedge cutting through the cosmos like a narrow piece of pie, thin but deep, reaching out billions of light-years. The slice contained thousands of galaxies. When the team plotted their positions in space, the pattern was unmistakable. The universe was not smooth. Galaxies traced long filaments, threads stretching hundreds of millions of light-years from end to end. Between the filaments lay voids, regions where almost nothing existed. The galaxies did not fill space evenly. They clung to the edges of emptiness. They outlined it. The map looked like a sponge, like foam frozen mid-rise, like the skeleton of something vast and patient that had been growing in the dark for longer than anyone had guessed. That first slice, published by De Lapparent, Geller, and Hutra in 1986, changed cosmology. It was no longer enough to ask how galaxies formed. Now we had to ask why they formed where they did. Why the threads? Why the voids? Why this shape and not another? The slice was narrow, a single cut through the sky, but it revealed that the universe had walls and filaments and vast hollow spaces, and that was enough to rewrite the questions we thought we were asking. The second CFA survey, led by John Hutra and Margaret Geller, ran from 1985 to 1995. 18,000 galaxies, each one a point of light measured, catalogued, and placed into the growing map. The survey expanded the slice into a thicker wedge, then into overlapping wedges, building volume. And in 1989, buried in that growing 3-dimensional atlas, the team found something larger than cosmological models said should exist. A supercluster so vast, it stretched across 500 million light-years. A concentration of galaxies so dense and so extended that it formed a wall, a boundary between regions of structure and regions of near emptiness. They called it the Great Wall. Not because it enclosed anything, but because it marked an edge, a place where the web thickened into something almost solid, a sheet of galaxies hundreds of millions of light-years long and wide, but only a few tens of millions of light-years thick. The Great Wall was a problem. Models of how the universe grew from its smooth early state, amplifying tiny fluctuations through gravity over billions of years, could not easily produce structures that large in the time available. Gravity worked slowly, density contrasts grew gradually. There had not been enough time for something that massive, and that extended to pull itself together. And yet the wall was there, traced galaxy by galaxy across the northern sky, undeniable. The universe, it turned out, had been building something we did not yet fully understand. By the time the CFA surveys ended in the mid-1990s, the cosmic web was no longer a hypothesis. It was a fact, mapped in detail across thousands of cubic megaparsecs of space. But a fact observed in one region of the sky is not yet a universal law. The question remained whether this was a local accident, a peculiarity of our neighborhood, or whether the entire observable universe was woven the same way. The answer came from scale. In the 2000s, two massive surveys set out to map not thousands but hundreds of thousands of galaxies across vast swathes of sky. The 2-degree field galaxy redshift survey conducted in Australia, and the Sloan Digital Sky Survey conducted in New Mexico. Where the CFA surveys had plotted thousands of galaxies in narrow wedges, these new projects plotted hundreds of thousands across wide fields. Where the CFA had covered slices, these covered hemispheres. The maps they produced were not cuts anymore, they were volumes. Deep, three-dimensional portraits of the universe stretching billions of light-years in every direction, dense enough to trace not just the brightest clusters but the faint threads connecting them. And everywhere they looked, the web appeared, filaments linking clusters like bridges between cities. Voids hundreds of millions of light-years across, nearly empty, their edges lined with galaxies like shores around an inland sea. Walls marking the boundaries of emptiness, sheets of light outlining the dark. The structure was not local, it was not an artifact of our position or our instruments. It was fundamental, universal, the large-scale architecture of everything. The 2-degree field survey mapped more than 200,000 galaxies. The Sloan survey mapped more than 1 million. Together, they confirmed what the first slice had hinted at in 1986. The cosmic web is not something that happens in one part of the universe. It is the way the universe is organized, at every scale we have been able to measure, from the nearest superclusters to the farthest structures visible in redshift space. What the first maps revealed was not chaos, it was order. An order we had not predicted, built by rules we were only beginning to decode. The cosmic web was not something imposed on the universe from outside. It was something the universe had made of itself, slowly, over more than 13 billion years, from seeds so faint they were barely fluctuations at all. The work of mapping continues. Each new survey adds depth, adds resolution, adds galaxies to the census. Instruments grow more sensitive. Telescopes peer deeper. The maps grow richer. But the shape itself has not changed since that first slice in 1986. Threads and silence, nodes and voids. A pattern that repeats at every scale we have measured, from clusters a few tens of millions of light-years across, to filaments stretching hundreds of millions of light-years from end to end, and voids even larger, hollow regions, where almost nothing shines. We did not expect the universe to have a shape. We expected it to be formless. A cloud of galaxies scattered by chance and by expansion, thinning with distance until the light grew too faint to see. What we found instead was architecture. The kind of structure that implies a blueprint. The kind of order that implies a cause, a mechanism, a history. The maps told us where the galaxies are. They showed us the web. But they did not by themselves tell us why. Why this arrangement and not another? Why threads instead of clouds? Why voids instead of a smooth thinning of density? The answer to that question was already waiting, written in the oldest light in the universe, in fluctuations so faint they were only a few parts per 100,000, ripples that would take 13 billion years to grow into the structure we see tonight. But that is another rung. For now, the maps are enough. They showed us that the universe is not a backdrop, it is a thing, a structure, a web spun across time, and we have spent 50 years learning to see it, galaxy by galaxy, thread by thread, void by void, until the shape became clear. The cosmic web has 4 parts, 4 textures woven together across 13 billion years. You might imagine the universe as a single substance, one kind of darkness stretched thin. But when astronomers began counting galaxies in 3 dimensions, they found that space itself has grain and direction. It has threads, it has crossroads, it has walls, and it has silence. The threads are called filaments. They are the long structures that connect one cluster of galaxies to another, stretching across distances that take light hundreds of millions of years to cross. A typical filament might span 200 million light-years from end to end, sometimes 300 million, a river of galaxies flowing through the dark. Some reach even farther, threading their way across 500 million light-years or more. The longest filament ever captured in a photograph, imaged by the Rosetta telescope in the glow of its own hot gas, stretches 50 million light-years from end to end. That single thread is wide enough to contain tens of thousands of galaxies, and it is only one strand in a web that fills the observable universe. The filaments are not uniform. They vary in thickness, in density, in the number of galaxies they carry. Some are dense streams, packed with bright galaxies flowing in loose formation. Others are tenuous wisps, barely visible against the background dark. But all of them share the same basic architecture. They are elongated, thread-like, stretching far longer than they are wide. They connect. They channel matter from one region of space to another. Where the threads meet, the web grows dense. These junctions are called nodes, though the word feels too small for what they are. A node is a galaxy cluster, a knot in the web where thousands of galaxies gather in a region 2 to 5 million light-years across. The gravity there is immense. The space between galaxies glows with gas heated to millions of degrees by the sheer weight of matter piled into one place. These are the cities of the cosmos, the places where the web is brightest. If you could stand at the center of a node and look outward, you would see filaments radiating away in every direction, threads of galaxies stretching toward other nodes, other crossroads, other knots in the web. Between the threads, the web stretches into walls. These are not barriers but boundaries, flattened structures of galaxies that curve around the edges of empty space. A wall might span 100 million light-years, a surface rather than a line, a place where the filaments have spread wide and thin. The walls are less dense than the nodes, less concentrated than the threads, but they are vast. They mark the places where the web folds back on itself, where one void ends and another begins. And then there is the silence. The voids. These are the places where almost nothing exists. A void is not truly empty, but it is as close to emptiness as the universe allows. A typical void stretches between 100 and 500 million light-years across, a sphere of near-nothingness larger than the distance light can travel in 500 million years. Inside a void you might find a handful of small galaxies, dim and scattered, drifting through the dark like dust motes in a cathedral. But mostly you would find darkness. No bright clusters, no rivers of stars, just the faint background glow of the universe itself, stretched across a volume so large that it defies the architecture of human thought. The voids are not rare. They are not the exception. They are the rule. Approximately 80% of the universe, measured by volume, is void. The web, the threads, the nodes, the walls, all the galaxies we have ever seen, all the light we have ever measured, all of it together, fills only the remaining fifth. Most of the universe by volume is almost empty. The web is the exception, and we live in it. But the web itself is mostly invisible. What we see when we photograph the night sky, when we map the positions of galaxies, when we count redshifts and plot them in 3 dimensions, what we see is only the surface. The galaxies are markers, tracers of something deeper. The true structure of the web is made of dark matter, the invisible substance that outweighs everything we can see by a ratio of 5:1. Dark matter does not emit light. It does not absorb light. It does not interact with anything except through gravity. But gravity is enough. The dark matter fell into place first, clustering along the faint density variations left over from the early universe, building a scaffolding in the dark. And then the ordinary matter, the gas and dust that would one day become stars and planets and people, fell into that scaffolding, like water condensing on a spider's web. The galaxies formed where the dark matter was densest. The filaments traced the paths where dark matter streams from one cluster to another. The voids are the places where dark matter is almost absent. The web we see is only the shadow of a deeper structure, a pattern written in invisible ink, revealed only by the way it bends space and gathers light. Even the ordinary matter we can see, the atoms that make up stars and planets, even that is mostly hidden. Approximately half of it is not in galaxies at all. It is stretched between them, filling the filaments with a thin hot gas that glows too faintly to photograph in visible light. This is the warm hot intergalactic medium, gas heated to temperatures between 100,000 and 10 million degrees. A plasma so diffuse that a volume the size of Earth's atmosphere would contain only a few dozen atoms. But across the length of a filament, across 200 million light-years, that diffuse gas adds up. Half the ordinary matter in the universe is invisible hot gas stretched between the galaxies, flowing along the threads of the web like sap through the veins of a leaf. So the web is not made of galaxies. The galaxies are only the visible part, the places where the invisible scaffolding is dense enough to collapse into stars. The web is made of dark matter and hot gas, of gravity and time, of structure that grew from almost nothing into the largest architecture in the universe. The threads are dark matter rivers, with galaxies strung along them like lights on a wire. The nodes are dark matter mountains, where galaxies pile up in the valleys. The walls are dark matter sheets, thin and wide, curving around the edges of the voids. And the voids are the places where the dark matter never gathered, where the web never formed. You cannot see the web directly, you can only see its effects. You can see the galaxies that mark its densest points. You can see the hot gas that glows in X-rays along its filaments. You can measure the gravity that bends light around its nodes. But the web itself, the dark matter structure that holds everything in place, that remains invisible. It is a map drawn in gravity, a shape that exists only in the way it pulls on everything around it. And yet we know it is there, we know its shape. We have measured it, galaxy by galaxy, void by void, thread by thread. We have traced its filaments across hundreds of millions of light-years. We have counted its nodes. We have mapped its walls. We have measured the silence of its voids. The web is not a theory. It is the shape the universe has taken, the architecture that emerged from the faintest ripples in the beginning. Threads and crossroads and walls and silence. 4 textures woven together, 4 parts of one vast structure. The threads carry galaxies like rivers carry stones. The crossroads gather them into brilliant clusters. The walls curve around the edges of emptiness, and the silence fills most of the volume, a background of almost nothing against which the web is drawn. Each part defines the others. Without the voids, there would be no filaments. Without the filaments, there would be no nodes. And somewhere in one of the threads, in a filament stretching between clusters, in a place where the dark matter is dense enough to hold galaxies but not dense enough to crush them together, there is a small spiral galaxy with 200 billion stars. We have climbed from the thread we inhabit to the structure that thread belongs to. And now we arrive at the rung where numbers stop behaving like numbers and begin to feel like distances you could fall through forever. This is the scale that breaks intuition. A single cosmic filament, one of the threads that weaves through the universe, can stretch for hundreds of millions of light years. Not thousands, not millions, hundreds of millions. If you could stand at one end and look down its length, the light you see from the far end would have been traveling toward you since long before the first stars formed in our galaxy. These are not rare outliers. Filaments of this scale are common throughout the observable universe, woven into the fabric of everything we can see. The universe did not scatter its matter randomly. It strung it along threads so long that their endpoints belong to different epochs of cosmic time. In 2020, the Rosetta telescope captured an image of the longest filament ever photographed directly. It spans 50 million light-years from end to end. That single thread, glowing faintly in X-ray light, is a bridge longer than the distance light can cross in 50 million years of uninterrupted flight. And it is just one thread, among countless others, most of them far longer, stretching through regions of the universe we have not yet mapped in enough detail to photograph. The filament Rosetta saw is not the longest that exists. It is simply the longest we have been able to render visible, to trace in a single unbroken line of light. The filaments are not solid. They are streams of galaxies, rivers of dark matter, corridors of gas, heated to temperatures that would vaporize anything made of ordinary matter in an instant. But they are real. They have shape, they have length, and that length defies the architecture of anything we know. There is no building, no bridge, no structure on Earth or in our solar system, or even in our galaxy, that prepares you for the idea of a thread 500 million light-years long. The mind reaches for comparisons and finds none. The filaments exist on a scale where metaphor collapses, where the only honest description is the measurement itself, rendered not as a number but as a journey no traveler could survive and no clock could measure. And yet the threads are not the largest feature of the web. The silence between them is. The voids, the near-empty regions that separate one filament from another, are not small gaps. They are not the spaces between stars, or even between galaxies. They are caverns in the structure of the universe itself. A typical void stretches for 100 to 500 million light-years across. 100 million light-years of almost nothing. No galaxies, no stars, no planets. Just hydrogen, thin and cold, drifting in a darkness so complete that if you could somehow stand in the center of a void and look in any direction, the nearest galaxy would be a faint smudge of light from an age you would never live to see end. The local void, the nearest of these great silences to our own galaxy, spans roughly 100 million light-years from edge to edge. It sits just beyond our local neighborhood, a hollow in the web close enough to map but too vast to ever cross. If the Milky Way were a single grain of sand, the local void would be a cavern large enough to swallow thousands of deserts. It is close, by the standards of cosmology. And it is a gulf we could never bridge, a silence we could never fill. This is the geometry we live inside. Threads hundreds of millions of light years long. Voids hundreds of millions of light years wide. And all of it, every filament and every void, woven into a single continuous structure that fills the observable universe from edge to edge. Light, which crosses the distance from the Sun to the Earth in 8 minutes, which reaches us from the nearest star in just over 4 years, takes 100 million years to cross a single void. 100 million years. Entire epochs of life on Earth have risen and fallen in less time. The voids are older than that. They have been empty since before the first stars lit the universe. They were hollow when the cosmic web was still forming, and they will remain hollow long after the last star has burned out. They are not temporary. They are not waiting to be filled. They are the architecture itself, the negative space that defines the positive, the silence that gives the threads their meaning. And the voids are not the exception. They are the majority. Approximately 80% of the volume of the universe is void, 80% silence. The web, the filaments, the galaxy clusters, the stars, the planets, everything we can see and everything we are made of, occupies the remaining 20%. We live in the exception. We live in the threads. We are not floating in the bulk of the universe. We are clinging to its edges, its rare dense regions, the places where gravity managed to gather enough matter to light a star. The rest is emptiness, patient and vast. The scale breaks intuition because it refuses to fit inside the models we use to understand space. We think of the universe as full. Full of stars, full of galaxies, full of light. But by volume, the universe is mostly empty. The web is the thin scaffolding that holds the small fraction of matter that exists at all. And even that scaffolding is vast beyond comprehension. The threads that seem so substantial when we count the galaxies strung along them are, in truth, narrow streams cutting through an ocean of nothing. The voids dominate. The silence dominates, and the web, for all its grandeur, is the rare exception to the rule of emptiness. If you could see the cosmic web from outside, if you could pull back far enough to watch the whole structure at once, you would see threads and knots and walls glowing faintly against an ocean of darkness. You would see the voids, vast and black, taking up most of the frame. You would see the filaments stretching between clusters like bridges across an abyss. And somewhere, in one unremarkable thread among billions, you would find us. A small node. A minor crossing. A place where one filament happens to pass through. We are not at the center of anything. We are in the middle of a thread, and the thread is one among countless others, and the structure continues in every direction farther than we will ever be able to see. But you cannot pull back that far. We are inside the web, we have always been inside it. And the only way to understand its scale is to map it, galaxy by galaxy, void by void, thread by thread, until the numbers accumulate into something that resembles a picture. The first maps showed only a few thousand galaxies. They were enough to reveal the pattern. The maps we have now show hundreds of thousands, and the pattern holds. The web does not change, it does not simplify or dissolve at larger scales, it repeats, faithful to itself, as far as we can measure. The longest filament ever photographed is 50 million light-years long. The longest filaments we have detected indirectly stretch 3 times that distance, perhaps more. The voids are wider still. And all of it, every thread and every silence, fits together into a pattern that repeats across the entire observable universe. Wherever we point our telescopes, we see the same architecture. Filaments, voids, clusters, Walls. The web does not end. It continues. Scale after scale, as far as we can see, and the evidence suggests it continues far beyond that, into regions we will never map. This is the rung where the mind begins to let go of the need to picture everything at once. You cannot hold the whole web in your imagination. You can only follow one thread at a time, trace one void, map one cluster, and trust that the structure continues beyond the edge of what you can see. The scale that breaks intuition is also the scale that teaches patience. The universe is larger than your ability to imagine it, and that is not a failure of imagination. It is simply the truth. The web is too vast to grasp all at once, and that vastness is not a barrier. It is an invitation to map slowly, to trace carefully, to accept that understanding comes not from seeing everything, but from seeing enough to recognize the pattern. The threads are hundreds of millions of light years long. The voids are hundreds of millions of light years wide. And we are inside one of the threads, mapping the web one galaxy at a time, learning the shape of the structure we have always lived within. The web was woven by time. 13.8 billion years of gravity pulling at a pattern that was, at the beginning, almost nothing at all. When the cosmic microwave background was released, light free to travel 380,000 years after the Big Bang, the universe was nearly smooth. Nearly. The temperature of that light varied from place to place by 1 part in 100,000. That was the difference. 1 part in 100,000 between where the web would grow and where the void would be. Those temperature variations mapped density variations in the matter itself. Regions slightly denser than average. Regions slightly emptier. The difference was so small that if you could have stood in the early universe and looked around, you would have seen nothing. No structure, no hint of what was coming. The universe at that moment looked like fog lit from within, featureless in every direction. But gravity does not need a large difference. It only needs time. The denser regions pulled harder on their surroundings. Matter flowed toward them. As they grew denser, their pull grew stronger. The emptier regions lost matter to their neighbors. They grew emptier still. Over millions of years, then hundreds of millions, then billions, the tiny fluctuations amplified. Dense became denser. Empty became emptier. The cosmic web began to take shape. Dark matter clustered first, unaffected by the radiation pressure that still buffeted ordinary matter in the early universe. Dark matter could fall freely into the densest regions. It formed the gravitational skeleton, invisible scaffolding that ordinary matter would later follow. Dark matter outweighs ordinary matter by roughly 5 to 1, so the scaffolding was strong. Where dark matter gathered, ordinary matter had no choice but to fall in after it. The web itself is mostly invisible. What we see, the galaxies, the stars, the light, are just the places where the invisible scaffolding is densest. The threads of the web are made of dark matter. The galaxies are droplets of ordinary matter that have condensed along those threads, like dew on a spider's web at dawn. This process did not happen all at once. The first structures to form were small. Clumps of dark matter a few million times the mass of the Sun, scattered across the young universe. Those clumps merged into larger ones. Larger ones merged into clusters. Clusters stretched into filaments as matter flowed along the paths of least resistance, following the gravitational channels carved by dark matter. Filaments connected at nodes. Walls formed where filaments intersected, creating boundaries hundreds of millions of light years across, and between all of it, the voids grew. The voids did not empty completely. A few galaxies still formed there, isolated and slow to evolve. But most of the matter drained away, pulled toward the filaments and the nodes. By the time the universe was a few billion years old, the basic architecture of the web was in place. It has been refining itself ever since. Galaxy clusters have grown denser, filaments have stretched longer, voids have expanded as the universe itself expands. Gravity is patient. It does not build quickly. But it does not stop. Consider what 13.8 billion years of amplification can do to a fluctuation of 1 part in 100,000. In the densest nodes today, the galaxy clusters at the intersections of filaments, matter is packed thousands of times denser than the cosmic average. Thousands of galaxies gather in a single knot, their light blending into a glow that spans millions of light-years. In the voids, the density can be 1/10 of the average, or less. A sphere of space 500 million light-years across might contain only a handful of small galaxies, adrift in near emptiness. The contrast between the densest and emptiest regions is now a factor of 10,000 or more. All of that contrast grew from a difference that was, at the start, invisible. The cosmic microwave background shows us the blueprint. The web shows us the building. Simulations have confirmed this. In 2005, a team at the Max Planck Institute for Astrophysics ran what was then the largest cosmological simulation ever attempted, the Millennium Simulation. It started from initial conditions matching the fluctuations observed in the cosmic microwave background. The simulation evolved 10 billion particles, each representing a clump of dark matter, forward through time. It applied only the known laws of physics: gravity, expansion, nothing else. When the simulation finished, the distribution of matter it had produced was a web: filaments, nodes, walls, voids. The structure matched the observed distribution of galaxies so closely that if you placed a simulated slice next to a real galaxy map, you could not easily tell them apart. This is not trivial. It means we understand the rules. The web is not mysterious in its origin. It is the inevitable result of gravity acting on tiny initial fluctuations over billions of years. Later simulations have refined the picture. Illustris TNG and its successor, Millennium TNG, published in 2023, cover volumes nearly 10 billion light-years across. They include not just dark matter but gas, stars, black holes, the feedback from supernovae, and the winds from active galactic nuclei. They simulate the full complexity of galaxy formation within the web. And they still produce a cosmic web that matches what we observe. The threads are in the right places. The voids are the right size. The galaxy clusters sit at the intersections where the simulations say they should. The computers can now reproduce the web. They start from quantum fluctuations in the first fraction of a second. They end 13.8 billion years later with something that looks like the universe we live in. This tells us that the web was not designed. It was not imposed. It grew. The structure we see tonight, the filaments hundreds of millions of light-years long, the voids that fill most of the volume, the dense knots where thousands of galaxies gather, all of it is the shadow of fluctuations so small they were almost nothing. 1 part in 100,000. Gravity heard it and spent 13.8 billion years turning it into architecture. Approximately half the ordinary matter in the universe does not live in stars or galaxies. It fills the space between them. Gas heated to temperatures between 100,000 and 10 million degrees, stretched along the filaments in a medium so thin and so hot that it is nearly invisible. We call it the warm-hot intergalactic medium. It glows faintly in X-rays. It is the flesh of the web. The galaxies are just the bones. The filaments are not empty tubes. They are rivers of hot gas flowing along dark matter scaffolding, carrying matter from the voids toward the nodes, feeding the galaxy clusters that sit at the intersections. The web is not static. It is alive with motion, with the slow gathering of matter along paths laid down billions of years ago. The web did not form around us. We formed because of it. Stars could not have ignited without the web. Galaxies could not have assembled. The filaments were the channels along which matter flowed. The nodes were the forges. Everything that exists today exists because gravity had 13.8 billion years to act on a pattern that was, at the beginning, 1 part in 100,000. You are not floating in a featureless void. You are inside a structure. That structure has a history. It began as a whisper in the cosmic microwave background, a map of tiny temperature differences in light that has traveled for 13.8 billion years to reach us. It grew, thread by thread, as the universe expanded and cooled. Dark matter fell into the densest regions first, building the skeleton. Ordinary matter followed, igniting into stars, gathering into galaxies, flowing along the filaments. The web will continue to grow, though more slowly now, as the acceleration of the universe's expansion begins to pull the threads apart. In the far future, the filaments will stretch and thin. The voids will grow larger. But tonight, the web is still here. Still intact. Still connecting every galaxy to every other. And the thread you are on, the filament that contains the Milky Way, the local group, the Laniakea supercluster, is one strand in a structure that spans the observable universe. The web was woven by time. Gravity did the weaving, and the pattern it followed was written in the first light. In 2005, a group of researchers at the Max Planck Institute for Astrophysics set a computer to work on a problem that had taken the universe 13.8 billion years to solve. They called it the Millennium Simulation. It began with the conditions of the early universe, a fraction of a second after the beginning, when space was filled with tiny ripples in density, variations so small they were almost nothing. The simulation applied only the known laws of physics: gravity, dark matter, time. 10 billion particles moved through a cube of space 500 million light-years on a side, pulled by forces that had been understood for centuries. The computer ran for weeks. When the simulation finished, the universe it had built looked almost identical to the one we observe. Threads of dark matter stretched across the void. Galaxies clustered at the intersections. Voids opened in the spaces between. The cosmic web had been reproduced from first principles, and it had emerged, not because anyone programmed it to look that way, but because the mathematics of gravity, given enough time, always weaves the same pattern. This was not a trivial result. It meant that we understood the rules. The web was not a mystery requiring new physics or hidden forces. It was what happens when you start with quantum fluctuations in the first moments of existence and let gravity do its work for billions of years. The simulation did not know what a galaxy was. It did not know what a filament should look like. It only knew how mass attracts mass, how dark matter clusters in the places where space is slightly denser, how ordinary matter follows the invisible scaffolding that dark matter builds. And from those rules alone, the web appeared. The Millennium Simulation tracked only dark matter, the invisible component that outweighs ordinary matter by a factor of 5 to 1. Dark matter does not emit light, it does not interact with radiation, it responds only to gravity, and that simplicity makes it the first thing to cluster in the early universe. Where dark matter gathers, ordinary matter eventually follows, falling into the gravitational wells like water pooling in the low places of a landscape. The simulation showed this process unfolding over cosmic time. At first, the distribution of matter was almost smooth, with only the faintest variations, echoes of those temperature differences in the cosmic microwave background that measured 1 part in 100,000. As time passed, those variations deepened. Dense regions grew denser, empty regions grew emptier. By the time the simulation reached the present day, the structure it had built matched the maps drawn from decades of galaxy surveys. Watching the simulation run was like watching a time-lapse of the universe growing up. In the earliest frames, matter spread almost uniformly, a faint mist with barely perceptible texture. Then the mist began to gather. Tiny clumps formed, pulling at the material around them. The clumps merged into larger concentrations. The space between them thinned. Filaments stretched between the densest regions, narrow bridges of dark matter connecting node to node. Voids hollowed out, their matter draining away into the surrounding walls and threads. The web grew sharper, more defined, until it became the structure we recognize today, a lattice of light and darkness spanning hundreds of millions of light-years in every direction. The Millennium simulation was not the end of the story. It was a proof of concept, a demonstration that the cosmic web could be understood as the inevitable outcome of known physics. But it left out much of the complexity. Real galaxies are not just dark matter halos. They contain gas that cools and collapses to form stars. They host black holes that inject energy back into their surroundings. They merge, collide, and reshape one another over time. To simulate all of that required a different kind of calculation, one that tracked not only gravity but also the behavior of gas, the formation of stars, the feedback from supernovae and black holes. Illustris TNG and its successor Millennium TNG, published in 2023, took on that challenge. Millennium TNG covers a volume nearly 10 billion light-years across, a cube of space large enough to contain thousands of superclusters, millions of galaxy groups, and countless filaments threading through the voids. It begins with the same starting point as the original Millennium simulation. The conditions of the early universe derived from measurements of the cosmic microwave background. But it follows the evolution of both dark matter and ordinary matter, tracking the cooling of gas, the ignition of stars, the growth of black holes, the winds driven by stellar explosions. It simulates the full life cycle of galaxies, from their formation in the densest nodes of the web to their slow drift along the filaments. When the simulation finishes, the universe it produces is not just structurally similar to our own, it is statistically indistinguishable. The galaxy distributions match those observed by the Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey, the Dark Energy Survey. The sizes of the voids are correct, the lengths of the filaments are correct, the masses of the galaxy clusters are correct. The cosmic web that emerges from Millennium TNG is not an approximation. It is a reproduction, built from the same initial conditions and the same physical laws that shaped the real universe over 13.8 billion years. The computers can now reproduce the web, starting from quantum fluctuations in the first fraction of a second, and ending 13.8 billion years later with something that looks like what we observe. This is the deepest kind of understanding, not just a description of what the web looks like, but a demonstration that we know why it looks that way, that we can build it from scratch using nothing but mathematics and time. The simulations do more than confirm what we already know. They allow us to see what cannot be observed directly. Dark matter is invisible, but in the simulations it is rendered in full detail, a vast network of filaments and halos that forms the skeleton of the web. The warm, hot intergalactic medium, the gas that fills the space between galaxies and holds approximately half the ordinary matter in the universe, glows faintly in the simulations, too diffuse to be easily detected by telescopes but clearly visible in the models. The simulations show how galaxies move along the filaments, pulled by the gravitational currents that flow through the web. They show how voids expand as the universe expands, pushing the filaments farther apart. They show how nodes grow at the intersections, accumulating more galaxies as matter flows inward along the threads. You can watch a simulated filament grow. At the beginning, it is barely there, a slight overdensity in the distribution of dark matter, a place where the invisible scaffolding is just a little thicker. Gas begins to accumulate along that line, drawn by gravity into the growing structure. The gas cools. Stars ignite. Galaxies form in clusters along the thread, like beads on a string. Over billions of years, the filament stretches, pulled by the expansion of space. But it never breaks. The galaxies within it continue to move along its length, flowing toward the nodes at either end, toward the places where multiple filaments meet and the web is densest. The fact that the simulations work is itself a kind of confirmation. The cosmic web is not a pattern imposed on the data by our instruments or our expectations. It is a feature of the universe that emerges naturally from the laws of physics, reproducible in a computer given nothing more than the initial conditions and the equations that govern the behavior of matter and energy. The web was not designed, it was not planned, it grew, thread by thread, node by node, over billions of years, and the computers can now reproduce that growth step by step. The simulations have become a tool for exploration. Researchers use them to test hypotheses, to predict what future surveys will find, to understand the processes that shape galaxies and the structures they inhabit. They run variations, changing the initial conditions or the strength of feedback from black holes, and watch how the web responds. They zoom in on individual filaments, following the flow of gas and the formation of stars in regions too distant or too faint to observe in detail. They zoom out to the scale of the entire simulation volume, watching the web as a whole, the vast lattice of matter and void that fills the universe from edge to edge. The cosmic web is no longer a mystery. It is a solved problem, a pattern we can reproduce, a structure we understand. The computers have shown us that the web is not an accident. It is the shape that matter takes when gravity has enough time to work, the architecture that emerges from the simplest rules applied over the longest spans of time. Far beyond the filaments we can map in detail, beyond the walls and the voids that make up the architecture of everything, there is a signal in the data that points to something larger still. It may be the largest known structure in the observable universe. If it is real, if the pattern holds, then it is a wall 10 billion light-years long, stretching across a tenth of the visible cosmos. Its name is the Hercules-Corona Borealis Great Wall, and its existence is both a discovery and a question that refuses to close. It was found in November of 2013, not by mapping galaxies one by one, but by watching where the universe dies. Gamma-ray bursts are the last light of collapsing stars, flashes so bright they can be seen across billions of light-years. A team led by Istvan Horvath, Jon Hakila, and Zsolt Baguli was studying the distribution of these bursts across the sky when they noticed something strange. In the direction of the constellations Hercules and Corona Borealis, the bursts were clustering, not randomly scattered, but gathered in a pattern, as if tracing the outline of something vast and distant. The bursts were coming from approximately 10 billion light-years away, from a time when the universe was less than a quarter of its current age. And the structure they seemed to outline was longer than anything that should exist. The estimated size, drawn from the positions of those gamma-ray bursts, was approximately 10 billion light-years from end to end. A wall of matter so large that light, traveling at its absolute limit, would take 10 billion years to cross it. To give that a shape you can hold in your mind, imagine the longest cosmic filament ever photographed. The one captured by the Erecita telescope, stretching 50 million light-years across space. Now multiply that length 200 times. The Hercules-Corona Borealis Great Wall, if it is a single structure, is not just larger than the filaments we have traced in detail. It is larger than the theory says it should be possible to build. The cosmological principle, one of the foundations of modern cosmology, assumes that on the largest scales the universe is smooth, homogeneous. No direction is special, no region fundamentally different from another. Structures can form, but only up to a certain size before the expansion of space and the finite age of the universe make further growth impossible. That limit, according to the models, is roughly 1.2 billion light-years. Anything larger than that should be extraordinarily rare, perhaps impossible. The Hercules-Corona Borealis Great Wall at 10 billion light-years is roughly 8 times that limit. Something that large should not exist, at least not according to the standard model of how the universe formed, and yet the data keeps pointing to it. In 2025, more than a decade after the original discovery, the same team revisited the data. They analyzed 542 gamma-ray bursts, refining the statistical methods, checking for errors, testing whether the clustering could be a coincidence. The new analysis suggested the wall might be even larger than first thought. The revised estimate, still under review, is that the structure may extend up to 15 billion light-years, approximately 50% larger than the original measurement. If that estimate holds, if the pattern is real and not an artifact of how we sample the sky, then the challenge to the cosmological principle deepens. A structure 15 billion light-years long would be not just improbable, but profoundly difficult to explain within the framework we use to understand how the cosmic web grows. But there is a caveat, and it is not a small one. The Hercules-Corona Borealis Great Wall was not discovered by mapping galaxies. It was inferred from the positions of gamma-ray bursts, which are rare, distant, and difficult to measure precisely. The bursts trace the locations of massive stars at the ends of their lives, and massive stars tend to form in regions of higher density, along filaments and walls. So a clustering of gamma-ray bursts could indicate a clustering of galaxies, a wall in the cosmic web. But it could also be a statistical fluctuation, a pattern that appears significant in a small sample but dissolves when more data arrives. Some astronomers have questioned whether the Hercules-Corona Borealis Great Wall is a single-bound structure, or whether we are seeing several unrelated filaments that happen to align along our line of sight. The data suggests a wall. The data does not yet prove it beyond all doubt. What we can say is this: if the Hercules-Corona Borealis Great Wall is confirmed as a single coherent structure, it is the largest known thing in the observable universe. Not the largest thing that exists, because we can only see as far as light has had time to travel, and the universe beyond that horizon is unknown to us. But within the volume we can observe, within the 13.8 billion light-years in every direction that make up the observable cosmos, nothing larger has been identified. It is a wall that spans a measurable fraction of the visible universe, a structure so vast that it challenges the assumption that the universe, at the largest scales, has no preferred direction, no special place. And it is not alone. The discovery of the Hercules-Corona Borealis Great Wall came after other large structures had already tested the limits of theory. The Sloan Great Wall, mapped in detail by the Sloan Digital Sky Survey, stretches approximately 1.3 billion light-years. The Close-Campusano Large Quasar Group, identified in the 1990s, is a concentration of quasars spanning roughly 2 billion light-years. Each of these structures pushed against the theoretical size limit. Each raised questions about how the cosmic web could grow so large in the time available. The Hercules-Corona Borealis Great Wall, if it is real, does not overturn those discoveries. It extends them. It suggests that the upper end of the cosmic web's architecture may be larger and stranger than the models predicted. The wall itself, like all the structures in the cosmic web, is not made of solid matter. It is a concentration, a region where the density of galaxies is higher than the cosmic average. The galaxies within it are separated by millions of light-years, just as they are everywhere else, but there are more of them per unit volume. aligned along a common axis, tracing the shape of a filament or a wall that formed over billions of years as gravity pulled matter into the densest regions. The wall is not a barrier. It is a thread in the web, larger than most, perhaps larger than any other, but still part of the same pattern that began with fluctuations 1 part in 100,000 in the early universe. What makes the Hercules-Corona Borealis Great Wall difficult to accept is not that it exists, but that it is so large. The cosmic microwave background, the light from 380,000 years after the Big Bang, shows us the seeds from which all structure grew. Those seeds were tiny, almost imperceptibly small variations in density. Gravity amplified them over 13.8 billion years, pulling matter into filaments and nodes, emptying the voids. But there is a limit to how much amplification is possible in that time. The universe has not been around long enough for gravity to build structures beyond a certain size. The Hercules-Corona Borealis Great Wall, at 10 billion light-years or more, appears to exceed that limit. It is not impossible. It is improbable. And improbable things, in a universe as large as ours, do sometimes happen. But they make us look twice at the models, at the assumptions, at the rules we thought we understood. The wall lies 10 billion light-years away, which means we see it as it was 10 billion years ago, when the universe was less than 4 billion years old. At that time, the cosmic web was still forming. Filaments were shorter, nodes less dense, voids less empty. The fact that a structure as large as the Hercules-Corona Borealis Great Wall could already exist at that early epoch makes it even harder to reconcile with the standard timeline of structure formation. It suggests that either the wall is not as large as the data implies, or that our models of how the web grows are missing something. Some process or condition that allows larger structures to form faster than we expected. For now, the wall remains the largest known structure, a feature in the data that has not gone away, but has not yet been mapped in the same detail as the filaments closer to us. Future surveys, deeper maps, more gamma-ray bursts, more galaxies measured and placed in three-dimensional space, will either confirm it or dissolve it. Until then, it stands at the edge of what we know, a reminder that the cosmic web, vast as it is, may contain threads and walls that stretch beyond the limits of our current understanding. The universe has a shape, it has always had a shape, and the largest known thread in that shape, if the data holds, is a wall 10 billion light-years long, woven in a time when the cosmos was still young, still assembling the architecture that would one day include us. Laniakea, our home supercluster, is itself one node in a larger web. The structure that contains 100,000 galaxies and stretches 500 million light-years across is not the final scale. It is not the end of the architecture. Laniakea sits at the intersection of larger filaments, a crossroads where threads of dark matter converge and galaxies gather in their billions. And somewhere in the outskirts of that supercluster, in a local cluster of a few dozen galaxies, the Milky Way turns slowly through the dark. We are not at the center of anything. We are not stationed at one of the great nodes where filaments meet and galaxy clusters blaze with thousands of members. The local group, the small collection of galaxies that includes our own and Andromeda and a handful of smaller companions, does not occupy a void. It does not sit in the deep silence between the threads. The evidence suggests we are in a filament, or very near one. We live in one of the connecting threads, not at a knot, not at a crossroads, not in the empty places. This is not a dramatic fact. It carries no revelation, no sudden shift in perspective. It is simply a location, a coordinate in the vast architecture. The Milky Way, with its 200 billion stars, its spiral arms and its halo of dark matter, is embedded in a thread of the cosmic web. That thread is hundreds of millions of light-years long. It connects nodes we have mapped, and nodes we have not yet named. And along its length, galaxies drift in the gravitational current like dust motes in a beam of light. The web is not something we look at from the outside. There is no vantage point beyond it, no place to stand and see the whole structure at once. Every observation we make, every galaxy we count, every redshift we measure is made from within the web itself. We are inside the pattern. The light that reaches our telescopes has traveled along filaments, across voids, through the architecture of the universe. When we map the cosmic web, we are mapping the structure that contains us. The thread we live in is not unique. It is one of countless filaments stretching across the observable universe, woven from the same dark matter, shaped by the same gravity, grown from the same tiny fluctuations in the early cosmos. There is nothing special about our location except that it is ours. The web does not care where we are. It formed according to laws that knew nothing of observers, nothing of consciousness, nothing of the questions we would one day ask about our place in it. And yet our place is not random. The filament we occupy is dense enough to have allowed galaxies to form. The node we belong to, Laniakea, is structured enough to have held those galaxies together. The thread is neither too empty nor too crowded. In the deep voids, where matter is sparse and galaxies are rare, there would be no stars, no planets, no long, slow accumulation of heavy elements. At the densest nodes, where galaxy clusters collide and merge, the environment is violent, unstable, flooded with radiation. We are in a thread, a place where matter gathered but did not crush itself, a place where structure formed but did not collapse. This is the paradox of the cosmic web. It is vast beyond comprehension, indifferent to our existence, built from forces that operate on scales we can barely imagine. And yet it is also the reason we are here. The web is not a backdrop to the story of galaxies and stars and planets. It is the story. The architecture came first. The threads were woven before the first stars ignited. The voids were already emptying when the universe was a fraction of its current age. Everything that followed, every galaxy, every star, every world, formed because the web gave it a place to form. We have spent 50 years learning to see the web. The first hints came in the late 1970s, when astronomers counting galaxies near known clusters began to notice patterns. The first maps came in the 1980s, when redshift surveys revealed walls and filaments and voids in the distribution of galaxies. The confirmation came in the decades that followed, as larger surveys mapped hundreds of thousands of galaxies, and the web emerged as a universal feature, not an accident of one region or one survey. And now, in the 21st century, we have simulations that can reproduce the web from first principles, starting from the conditions of the early universe, and evolving forward through 13.8 billion years of gravity. The web is no longer a hypothesis. It is observed, measured, mapped, and we know where we are in it. Not at the center, not at the edge, not in the silence of the voids or the blaze of the great nodes. We are in a thread, one strand in a structure that fills the observable universe, one filament among millions, one small node in a supercluster that is itself just one node in a larger pattern. The thread we live in has no name that would mean anything on the scale of the whole web. It is not one of the Great Walls. It is not the Hercules-Corona Borealis structure or the Sloan Great Wall, or any of the vast features that stretch billions of light-years across the sky. It is a local thread, a regional filament, a strand in the part of the web we happen to occupy. And that is enough. That is all it needs to be, because the web is not a hierarchy. There is no most important filament, no central node, no thread that matters more than the others. Every part of the web is connected to every other part. Every filament leads somewhere. Every node is a crossroads. The thread we live in connects to other threads, which connect to others still, which reach across the universe in a network that has no beginning and no end, only structure. You are inside that structure now, not metaphorically, not as a thought experiment. You are physically embedded in a filament of the cosmic web. The atoms in your body, the planet beneath you, the star that warms it, the galaxy that holds that star, the local group that holds that galaxy, the supercluster that holds that group, all of it is part of the thread. All of it belongs to the web. The web is not something distant. It is not something you observe from outside. It is the architecture you live in, the scaffolding that made everything possible. And tonight as you rest, the web continues. The filaments stretch, the voids expand, the nodes gather their galaxies. The dark matter holds the structure together. Gravity pulls, time flows, and somewhere in the outskirts of Laniakea, in a thread that has no name, a small galaxy turns. The web did not form around you, you formed because of it. Every thread leads somewhere. That is the promise of a web. Not that every thread is equal, or that every thread is known, but that none of them simply ends. A filament stretching 300 million light-years across the dark does not terminate in silence. It meets another filament. It joins a wall. It frames a void. Somewhere at the far end of that thread, gravity is still pulling galaxies into place. You have spent the last hour tracing the architecture of the universe. You have seen how it was discovered, mapped galaxy by galaxy, in slices of sky that revealed walls where smoothness was expected. You have learned what it is made of. Nodes where thousands of galaxies gather, filaments that stretch farther than light can travel in 100 million years, walls that curve around voids so vast they occupy most of the volume of everything. You have watched simulations begin with quantum fluctuations smaller than an atom, and end, 13.8 billion years later, with a web that matches the one we observe. You have considered the Hercules-Corona Borealis Great Wall, the largest known structure, a thread so long it challenges the models that predicted the web itself. And you have found your place in it, not adrift, not lost, but located. One small galaxy, in one supercluster, in one filament, in a web that was woven before the first star ignited. The cosmic web is not a metaphor. It is not a poetic flourish or a visual approximation. It is the actual large-scale structure of the universe, the shape that matter takes when gravity has 13.8 billion years to work. The threads are real. The voids are real. The intersections where filaments meet and galaxies pile into clusters 10,000 strong are real. And the silence between them, occupying 4/5 of the universe by volume, is real as well. The web is not something imposed on the cosmos by our need to see pattern. It is what the cosmos is. Every thread in that web began as a ripple, a fluctuation in density so faint that the cosmic microwave background, the most precisely measured relic of the early universe, shows it as a variation of 1 part in 100,000. Regions that were slightly denser by that invisible margin pulled harder on the matter around them. Regions that were slightly less dense lost matter to their neighbors. Dark matter clustered first, unimpeded by radiation, building the invisible scaffolding. Ordinary matter followed, falling into the gravitational wells that dark matter had carved, lighting up along the threads like dew on silk. The voids did not empty all at once. They drained slowly, over billions of years, as galaxies migrated toward the filaments, and the filaments thickened into walls. What you are resting inside tonight is the result of that process. Not its beginning, not its end, but its present form. The web is still growing. Filaments are still drawing galaxies inward. Voids are still expanding as the universe itself expands. The Hercules-Corona Borealis Great Wall, if it is confirmed as a single structure, is still 10 billion light-years away, and the light we see from it left when the universe was less than a quarter of its current age. The web we observe is not the web as it exists now. It is the web as it was, averaged across billions of years of light travel, a fossil record written in redshift. But every thread in that fossil record leads somewhere. The filament that contains the local group, the small collection of galaxies that includes the Milky Way and Andromeda, connects to other filaments. Those filaments frame voids and join at nodes. Those nodes belong to superclusters. Those superclusters are woven into the larger web, the one that fills the observable universe with structure on every scale we can measure. There is no edge to the web within the volume we can see. There is no point where the threads simply stop. The web continues beyond the horizon of observation, into regions of space whose light has not yet had time to reach us, and it will continue beyond that, into regions we will never see, because the expansion of the universe is carrying them away faster than light can cross the distance. You are not outside that structure looking in, you are inside it. You have always been inside it. Every atom in your body was forged in a star that belonged to a galaxy that belonged to a filament. The calcium in your bones, the iron in your blood, the oxygen you are breathing as you listen to this, all of it condensed from gas that fell along a thread of dark matter billions of years ago, drawn by gravity into a region dense enough to collapse and ignite. The web is not a backdrop to your existence. It is the condition that made your existence possible. A cartographer's job is not to invent the territory. It is to render it faithfully, to give every feature its place on the map, to show what connects to what. The cosmic web has been mapped now, in enough detail that we know its rules, its scales, its history. We know that it grew from fluctuations we can measure. We know that simulations starting from those fluctuations reproduce the structure we observe. We know where we are within it, one small node, in one long thread, in a web that took 13.8 billion years to weave. The web did not form around you. You formed because of it. Every galaxy in every filament is part of the same pattern. Every thread leads somewhere. And tonight, yours leads here. Rest. You are not floating in empty space. You are caught in a web. The universe has a shape. It has always had a shape. And tonight, you are inside it. For most of human history, we imagine the cosmos as a scattering of lights across darkness, galaxies thrown at random through an infinite void. But when astronomers finally mapped enough galaxies to see the pattern, they discovered something else. The universe is not a featureless void. On the largest scales, matter is organized into a vast network of threads and crossroads, sheets and silence. This is the cosmic web. The Milky Way, with its 200 billion stars, is one small node in that network. Most of the universe, by volume, is almost empty. The web is the exception. And we live in it. Lower the lights, put on your headphones. The first hints came from counting galaxies near known clusters in the late 1970s. Astronomers pointed their telescopes at regions where galaxies seemed to gather, and began to notice something strange. The galaxies clumped. They formed chains. And between those chains there was almost nothing. But hints are not maps. To see the web, you need distance. You need to measure not just where a galaxy sits in the sky, but how far away it is, how its light has been stretched by the expansion of space itself. You need redshift. In 1977, a team at the Center for Astrophysics began the first systematic attempt to map the universe in 3 dimensions. They measured the redshift of galaxy after galaxy, one spectrum at a time. The work was slow. But by 1986, they had enough data to plot a single slice of sky containing thousands of galaxies. And in that slice, the web revealed itself. The galaxies were not scattered. They formed walls, long, thin filaments, clusters at the intersections, and between them, vast regions where almost no galaxies existed at all. The universe had structure, not the smooth distribution that theory predicted, but something intricate, something that looked almost biological in its complexity. In 1989, the same survey found something even more unsettling. A wall of galaxies stretching across 500 million light-years of space, a supercluster so large that the models of the time said it should not exist, and it was only the beginning. Over the next 2 decades, larger surveys mapped hundreds of thousands of galaxies. Each one confirmed what the first slice had shown. The web was not an accident of one region of sky. It was everywhere, a universal feature of the cosmos, as fundamental as the expansion of space itself. But what is the web made of? There are 4 kinds of structure woven into the same fabric. First, the crossroads. Nodes where filaments intersect, dense clusters of thousands of galaxies bound together by gravity, each cluster a few million light-years across. These are the bright knots in the web. Second, the threads. Filaments stretching between the nodes, elongated rivers of galaxies flowing along invisible channels. These are the strands that give the web its name. Third, the walls. Flattened sheets of galaxies forming boundaries, surfaces that curve and fold through space, marking the edges of something else. And fourth, the silence. Voids. Regions where almost no galaxies exist, enormous hollows in the structure of space itself, hundreds of millions of light-years across. These voids occupy roughly 4/5 of the universe's volume. Most of the universe by volume is void. The web is the exception. And we live in it. But the web itself is mostly invisible. What we see when we look at a galaxy map are not the threads themselves, but the places where the invisible scaffolding is densest. The filaments are made primarily of dark matter, the unseen gravitational skeleton that shapes the cosmos. Gas and galaxies accumulate along those dark matter structures like droplets of water condensing on silk. Where the dark matter is thickest, galaxies form. Where it is sparse, there is only emptiness. And between the galaxies, stretched along the filaments, is something else. Approximately half the ordinary matter in the universe is not in stars or galaxies at all. It is invisible hot gas threading the space between them, heated to temperatures between 100,000 and 10 million degrees. The warm hot intergalactic medium. The blood in the veins of the web. The scale of it breaks intuition. Individual filaments commonly stretch across hundreds of millions of light-years. The longest ever photographed, captured in X-ray light by the Rosetta telescope, spans 50 million light-years from end to end. That is not the longest filament. It is only the longest we have managed to image in a single frame. The voids are larger still. A typical void has a diameter of 100 to 500 million light-years. The closest void to the Milky Way, the local void, is roughly 100 million light-years across. If you could stand at its center and look in any direction, you would see almost nothing. A handful of dwarf galaxies scattered across a volume that could hold tens of thousands. Silence. Stretched across a distance light takes 100 million years to cross. And the web did not exist at the beginning. 13.8 billion years ago, the universe was smooth. Not perfectly smooth, but close. When the cosmic microwave background was released, 380,000 years after the Big Bang, the temperature of the universe varied from place to place by only 1 part in 100,000. One region might be 100,000th of a degree warmer than the cosmic average, another 100,000th of a degree cooler, 1 part in 100,000. That was the difference between where the web would grow and where the void would be. Gravity did the rest. Denser regions attracted more matter, As they grew denser, they attracted even more. Underdense regions lost matter to their neighbors. As they emptied further. Over billions of years, the tiny ripples in the early universe were amplified into the cosmic web we observe today. Dark matter clustered first. Unaffected by radiation pressure, free to collapse under its own gravity, it formed the invisible skeleton. Ordinary matter fell into the dark matter structures, pooling in the deepest gravitational wells, forming the first stars, the first galaxies, the first filaments. The web was woven by time. 13.8 billion years of gravity, pulling at a pattern that was 1 part in 100,000. And we know this not only because we observe it, but because we can reproduce it. In 2005, a simulation called the Millennium Simulation started from the conditions of the early universe and applied only the known laws of physics. 10 billion particles representing dark matter evolved forward through cosmic time. The simulation ran for weeks on some of the most powerful computers on Earth. And when it finished, the result was a web almost identical to what we observe. This is not trivial. It means we understand the rules. The simulations have only grown more sophisticated. Illustris TNG, Millennium TNG. Volumes nearly 10 billion light-years across, including not just dark matter, but gas, stars, black holes, the full complexity of galaxy formation. And they produce galaxy distributions consistent with the larger surveys we have conducted. The computers can now reproduce the web, starting from quantum fluctuations in the first fraction of a second, and ending 13.8 billion years later, with something that looks like what we observe. The web is not a mystery, it is a consequence. But there is one structure that troubles the picture. The largest known structure in the observable universe was discovered in 2013. Not by mapping galaxies, but by mapping gamma-ray bursts, the brilliant flashes of light released when the most massive stars collapse. A team of astronomers noticed an unusual concentration of these bursts in the direction of the constellations Hercules and Corona Borealis, roughly 10 billion light-years away. They called it the Hercules-Corona Borealis Great Wall. If the data is correct, if the concentration of gamma-ray bursts truly traces a single coherent structure, then the Great Wall is approximately 10 billion light-years in length. A re-examination published in 2025 suggests it may be even larger, perhaps 15 billion light-years, something that large should not exist. At least not according to the Standard Model. The cosmological principle suggests that structures larger than about 1.2 billion light-years should be extremely rare. At 10 billion light-years, the Hercules-Corona Borealis Great Wall is roughly 8 times that limit. And yet the data keeps pointing to it. Some astronomers have questioned whether it is a single-bound structure or a statistical artifact, a chance alignment of unrelated bursts. The identification is based on gamma-ray burst statistics, not direct galaxy mapping. But if it is real, if it is a single structure, then it is the largest known thing. A wall of galaxies and dark matter, stretching across 1/10 of the observable universe. And even that is only a thread. We are in the web. We have always been in the web. Laniakea, our home supercluster, 500 million light-years across, containing 100,000 galaxies, is itself one node in a larger web. The local group, which includes the Milky Way and Andromeda, sits in or near a cosmic filament, not in a void, not at a major crossroads. We are in a thread, not a knot. You are not floating in empty space, you are caught in a web that took 13.8 billion years to weave. A web grown from the faintest ripples in the early cosmos, 1 part in 100,000, amplified by gravity, into the largest structures in the universe. The web did not form around you. You formed because of it. Every atom in your body was forged in a star that formed in a galaxy that sits on a filament of dark matter that grew from a fluctuation in the cosmic microwave background. A cartographer's job is to give things their place on the map. Tonight, your place is this: one small node, in one long thread, in a web that took the lifetime of the universe to grow. Every galaxy, in every filament, is part of the same pattern. Every thread leads somewhere. And tonight, yours leads here. Rest. A line across the map. You have traveled through the web tonight, mapped it galaxy by galaxy, traced its filaments across hundreds of millions of light years, watched it grow from ripples too faint to see into the architecture that holds everything together. That journey mattered, not because the web is beautiful, though it is, but because now you know where you are. You are not adrift, you are woven in. Some of you heard every word. Some of you fell asleep somewhere in the 3rd billion light years, and that is exactly as it should be. The dark will still be here. So will I. Wherever you are tonight. One small world, in one quiet thread, in a web 13.8 billion years old. Rest easy. Tomorrow night, if you'd like, come back. There are other structures to walk through together. Every thread leads somewhere. Sleep now.